Hello, everyone. Welcome to the second day of the Optiwave webinar. I'm Ahmed Abu Mazwood. I'm a staff scientist at CMC Microsystems. So today, Optiwave team will talk about the OptiSPICE Tanner Plugin. Our speakers for today, Chem Bonfil. Chem is a product manager of OptiSPICE and Optiwave, and Saurabh Bedi, application engineer, OptiSPICE team at Optiwave.
Thanks, Ahmed, for the introduction. This is Jem speaking from Optiwave. I am the product manager of OptiSPICE. I will be talking about OptiSPICE a little bit, give you a background info before passing the presentation on to Saurabh, who is going to be showing you how the OptiSPICE plugin works together with Tanner. Now, OptiSPICE is an electro-optic simulation tool where it's taking its roots from the standard SPICE. Standard SPICE is initially designed for for electrical integrated circuit simulation. So it has a set of linear and nonlinear electrical devices like RLC circuits, voltage sources, inductors and capacitors. And then it also has nonlinear devices like BJT, MOSFET. So at the end, like I said, it's designed for doing a transient and frequency domain simulation of electrical integrated circuits. Now, with OptiSPICE, what we have done is we have taken this basis and we have built an optical infrastructure on top. What it enables the SPICE is to handle optical devices at the same time as electrical devices. So you can do your electro-optic circuit simulations within the same simulation engine. And it's also enabled, it also allows time and frequency domain simulations as well, like any other standard SPICE. The optical devices, again, range from linear to nonlinear. So we have multi-mode, multi-channel devices. All the devices support this mode of operation. You could have, for linear devices, it could be splitter, joiner, SParameter models. For the nonlinear model, we have lasers, optical fibers, and other devices you can think of. So we have one of the main strengths of OptiSPICE in general is how it handles electro-optic circuits with reflections and also as well as feedback loops. Because everything resides within the same simulation engine, it is very good at handling feedback loops without going unstable. So you can do transient simulations of your electro-optic devices. It is very good at doing link simulations because we can do electronics at the same time as optics. So you can have your laser driver, you can have the driver circuitry, you can have the optical fiber, and then on the other end, the receiver circuit with a photodiode and a TIA and a limiting amp, for example. So now today we're mostly going to focus on the plugin version of OptiSPICE, which was developed later. And the main purpose of that is to better support photonic IC design. We have collaborated with Tanner to add our optical simulation capabilities to their environment. So it works on top of TSpice, which is the standard SPICE simulator for Tanner. They have an API that we connect to. And then the resulting approach is that it is a seamless integration between two software. What I mean by seamless is that you're going to see in a moment, we'll be using the Tanner's user interface. And we have defined within that user interface our OptiSPICE libraries. And then it allows us to run optical and electrical simulations like the same way we were running with the standalone. So you can take advantage of all the capabilities of Tanner, and now you have optical simulation capabilities added on top. For example, if you would like to do an optical simulation of a chip, and this is one of the main strengths, You can do your layout in SEdit, extract the circuit, and then do your test bench and create the simulation for that chip, and then look at the performance. The other thing we're doing is we're also collaborating with EDA vendors so that we support their PDKs. So we have verified optical models. When you receive the PDK and you want to design, as a designer, you're interested in designing an IC circuit, for example, you receive a PDK, and you can also at the same time receive the integrated circuit library for optical devices that have already been tweaked to work with OptiSPICE software. So this completes the whole circuit of the whole workflow for photonic integrated circuit design. So now I'll let Saurabh take over from here and show you the integration we have done with Tanner.
Thank you, Chem. Hello, everyone. Today, as Chem mentioned, I'll be taking you through the workflow of the OptiSPICE plugin, which is seamlessly integrated with the Tanner platform. I'll be beginning by showing you the what all libraries comes with the Tanner suite, and how we can load those libraries, whether they're electrical or the OptiSPICE optical device libraries, into the Tanner. So firstly, let's say a user installs the Tanner, then in the documents directory, you will have a Tanner EDA folder, and then you will go further to in the version installed, and then you will see, let's say you go to the process here, and in the JPEG, you will see the standard JPEG libraries, I mean the general photonic integrated circuit library. So here you can see all the optical devices like bands, and then compact Y branches, some bond pads as well, crossings, directional couplers, different kinds of waveguides, grading coupler, etc. So this is the standard JPEG library. Then also with the Tanner, we have the user gets the other electrical libraries. For example, here in the standard libraries, we can see the devices, like all kinds of capacitors, resistors, different kinds of JFETs, MOSFETs, BGTs, etc., etc. Then also we have a library for different elements which are used for plotting the current and voltage and different kind of and for doing the different kind of analysis. So for all the kinds of plots, we have different elements here. Then we have sources as well, like we have the pulse sources, laser sources, some bit generators, various kind of. So these are all electrical library which comes with the Tanner. And along with these, the one which are integrated by OptiSPICE can be seen here in the third party in Optiwave. And if you go to the OptiSPICE devices, so here we have the folder of OptiSPICE devices and the OptiSPICE circuits. If you go to the OptiSPICE devices, you will see here all the optical elements which are being modeled and integrated by the OptiSPICE plugin into the Tanner. So these are all optical devices. Like we have the lasers, voltage control, frequency control. We have all different kinds of optical elements like circulators, filters, isolators, phase shifters, etc. And different kinds of waveguides, waveguide crossings, and also we have the SParameter elements to load the SParameters and carry out your circuit level your circuit level simulations. So these are all the optical devices which comes along with the OptiSPICE integration. As well as the user gets the OptiSPICE circuits. There are certain circuits which are already pre-packaged and tested with the Tanner platform. So the user can always go through these different circuits for AC and some frequency simulations and some transient time domain simulations and some complex simulations like for the fiber optic gyroscope, which is a very good example to show how our OptiSPICE plugin can handle the feedback loops and the reflection as well. So all these kinds of examples are also present here. And now I'll be quickly telling you how we can integrate all these libraries into the Tanner. So let's say, so when the Tanner suite is installed, the user generally gets a library definition file, which looks like this. If I just open and show it to you, so here, so this is the library definition file, and if you see here, we are defining the JPEG here. So we have, so basically we have added the path, this whole path for the JPEG library, which I just showed you, and the standard library, and then we assign that JPEG library. And then also we are including another library definition file. And this particular library definition file includes all the standard electrical device libraries, which I just showed you, like the devices, some miscellaneous, the SPICE sources, and the plot, and etc. As well as it includes our OptiSPICE optical device library, OptiSPICE devices, and OptiSPICE circuits. There's also one extra library which is named as my circuits. Like this is a library which I have created for myself, and just like this one, like user can always create their own libraries, and you can add it to your to this library definition. So this is your library definition for all your different libraries, including this JPEG one. And now let's say we start with the SEdit, which is the schematic and simulator tool for the Tanner. So if I open the SEdit here, then we hit open, and then this is that library definition file. If I open it, and here you will see on the left hand side in the libraries window, you will see all kinds of libraries which I just showed you: the devices, JPEG, miscellaneous, SPICE plot, sources. Here you will see all the elements below, as well as it includes the optical device library included by OptiSPICE. So these are the OptiSPICE device library. Here you can see all the optical elements, as well as you can see the OptiSPICE circuits here. So all the circuits, so all the folders which I just showed you, they are all present over here. So this is basically a standard schematic editor and simulation window. Now, let's say if you want to create a new schematic in the Tanner, maybe if some of you are familiar with the Tanner, then you will know how to create a new schematic and how to create a new sub-circuit. But I'll be going through, I'll be telling you in brief about how we can create a new schematic. So let's say this is my library, my circuits, and I want to create a new circuit. So I'll just right click here, and I'll open a new view. And in the new view, make sure you select the particular library where you want to save your schematic. In this case, it will be my circuits. Then we have to name your circuit, let's say test 11, for example. And then in the view type, you have to make sure you select schematic because you are creating a schematic. We'll come to symbol and SPICE to later on in this in this tutorial. But for now, since we are creating a schematic, you will select a schematic from the drop-down menu and hit OK. So this will create your schematic window over here. And if we look in the My Circuit, so this is it's highlighted. This is your test 11 schematic, and the basic functionality of this Tanner platform is it's just like any other simulating software, like I showed you for the OptiSPICE standalone. Let's say we have to create a circuit, we can just drag and drop our devices over here, and we can make the connections and everything by using the wire. So this is the wire. We just have to connect the circuits, and that's it. Once you that's how you basically drag and drop and make your schematics over here. So you can see all the libraries on the left, and let's say if you click on any of the element, let's say for example laser, on the right hand side in the properties section, you will see the properties of that particular element. In this case, we have the units for the laser. You can select whichever unit you want. Then we have the frequency value, and then in the input type, let's say we have whether you want to send a power in the phase, or you want to send polar or Cartesian form. And yeah, so that's it. Here on the right hand side, you will have a properties window. At the center, here is your schematic, and on the left hand side, you will see all the libraries and their corresponding elements over here. Now, I'll be going through deeper into different kind of simulations and different kinds of schematics which are built, and all these schematics which I'll be showing you today, they all comprises of elements from the JPEG library, which is the standard one, this one, and as well as the devices from our OptiSPICE device library. So all the circuits which I'll be showing you today include these. As Chem mentioned earlier, like and as well as yesterday, that there are certain PDKs also which are very well modeled and tested with the Tanner platform, but I won't be going through any PDKs today. So we'll just use the JPEG standard library and our OptiSPICE device library. Now, beginning with the AC simulations, so I'll be going through this example. So in this AC simulation example, like what you see over here is basically a second order ring demultiplexer filter. So we have we have 4 second order rings, and these rings comprises of elements like directional couplers or cross coupler from the JPEG library. If I select this one, on the right hand side in the properties, you can see the standard parameters like the gap and the coupling length, and you can see the library which is present over here, and the type of waveguide, which is strip waveguide. So for the directional couplers, I would like to bring your kind attention to this thing, that these directional couplers are basically modeled in such a way internally that by changing the length of here, by changing the coupling length here of the directional coupler, we can tweak the coupling coefficient or the power coupling ratio. So it is modeled in such a way internally that if we change the length, we can change the coupling coefficient, and the gap, it stays constant over here. So for, let's say we want a 50-50 splitting ratio for this coupler. So for 50-50, we have this corresponding length of 46.64 micron. And same way, if you want to change the coupling coefficient for this direction coupler, I have a different length over here. And to formulate the ring, I'm using waveguides, straight waveguides from the JPEG library. And here you can see in the length section, I have defined the different lengths for each of the waveguides over here. So this way, like this whole filter is basically comprises of just two elements, cross coupler and waveguide. And here we have a laser source, which will be sending in the laser, which will be sending in the signal through the filter. And it's a voltage control laser. And to control this laser, we have a AC voltage source, and it's connected to the ground. So in the laser, if you see, we have set the channel units to terahertz, and the channel values is 193.1 terahertz. Now, since we are, other thing is, like, to measure the response, we are using the optical probe. So if I select this optical probe, these optical probes are taken from our optical device library, this one. And we are also using the terminators over here to terminate the signal. So whenever you use the optical probe, you have to make sure, like in this case, it is connected to this terminator. So you have to make sure that you mention the name of the device to which the optical probe is connected. Like in this case, I have given it the name O terminator 2 because that's the name of this terminator here, O terminator 2. So I've given the device name O terminator 2, and then you have to choose the correct direction. Like in this case, the signal is coming from this port into the terminator. So you have to, in the direction menu, you have to choose in here. Let's say if this optical probe is connected to this port of optical 4, of opt4 port of the directional coupler, then you will be choosing out direction here. And also here in the port, you need to mention that particular port. But since in this case it is connected to the terminator, so I'll be setting the direction in. Since the signal is coming into the terminator, and I've mentioned the port 1, and that's the default. So and in the same way, optical probes are connected to all the rings to measure the response coming out of those rings. And once the circuit is complete, then we hit the setup simulation button here. This will open the simulation window. Here you will see all the different properties. Like for example, you have in the general section, you have an option of mentioning the SPICE file name. Then we can include the different files. Like in this case, I have included the OptiSPICE header file. I'll come to that later. What is this OptiSPICE header file? And also you can include the other library files as well. Then we have some simulation options, net listing options, hierarchy, priority. Then we have some additional SPICE commands. Like if your simulation is not converging properly, there are certain SPICE commands which help you to converge your simulation. So then those can be added over here. Then here we can add the list of parameters. And then further, there are different kinds of simulations like DC operating point analysis, transient analysis, DC sweep, AC analysis, and temperature parameters used, etc., etc. So we won't be going through all of them today. We'll be going through a couple of like AC analysis and the transient time domain analysis. So for this particular example, since we are running the AC analysis, so I'll be selecting the AC analysis simulation, and in here I'll set the sweep type to linear, and then we can you can choose whatever, like whether you want logarithmic decade or octave, or you want to set the list of frequencies, you can do that. But I'll choose the linear, and then I'll set the frequency range and number of frequency points. And once your simulation is set up, then you hit run simulation. Now, once the simulation is run, this will this SEdit window, it will open another window, which is the TSpice window, which is this one. And but for now, like as you can see here, it shows some warning and shows some 6 fatal errors. I'll be telling you what are these fatal errors. So this opens up this window once the simulation is completed, and this is a TSpice window. And before I move further, one important thing I'd like to tell you over here is every time a user installs the Tanner and before running your simulations for the first time, you need to load the Tanner API file. This API file is basically, it's a .dll file which includes the codes of all the optical devices which we have modeled. So it contains the information that the way each of the optical devices are modeled and handled, all the set of equations and everything. So those are all included in the Tanner API file, and that Tanner API .dll file has to be uploaded here. It has to be selected. So we'll go to the setup application. And in the setup application window, we'll go to external programs. And here in the optical simulator.dll, I have mentioned the path for that particular Tanner API file. If you see, so here is the Tanner API.dll file. If you don't select that, then it won't recognize the optical devices. So once you have uploaded it, I mean, you have mentioned the correct path for that file, you uploaded that, you hit OK, and that's it. So this thing has to be done only once, right after the installation. And after that, once you have uploaded, then you don't need to do it next time. Now, coming back to this simulation, so we started the simulation and it's showing the errors. Now, what's happening here is from the SEdit, whenever you hit run, what it does is it extracts netlist and then it runs from the netlist. Now, for some reason, there is a bug in the Tanner platform at the moment, and we are working to correct this bug. So what it does is, like, when it extracts the elements in the netlist, for some reason it is missing a semicolon definition. I'll show you what I mean. So to extract the netlist for any circuit, you hit this T button over here. So when you select that, it will open your netlist. So this is the netlist for this particular circuit. So you can see all these settings. Like, I have included the header file. There are 4 different probes, and here's the list of all the elements over here, all the directional couplers and the straight waveguides and everything, and then there's a simulation settings as well. So this is your complete netlist, which is extracted. Now, what's happening over here is, for some reason, for the JPEG devices, it is missing a semicolon. It's missing the inverted commas over here. So if we just put it here, we don't have to put it for all of them. Just one for the directional coupler and one for the straight waveguide. And if we do this, that's it, and then we can save it, and we run the simulation. We can also run the simulation from here. So now this will open another window, which is the Tanner waveform viewer. So this is the Tanner waveform viewer. And now, as you can see, the simulation is completed. And here is the transmission response coming out of those ring DMUX filter. So the whole purpose of this filter is to basically filter out 4 different channels. And since it's a second order ring filter, so the response you will see is a kind of flat top. So this will filter out 4 different frequency channels. So this is channel 1, channel 2, channel 3, and channel 4. So that's the response for your ring DMUX. So and on the x-axis you can see the frequency sweep, and on the y-axis you have your transmission in dB. Also, it shows the phase over here for your response. So that's the AC simulation, and that's how you set up your schematic, like you create your schematic and you set up your simulations and everything. Now, this was an AC simulation. Now I'll be moving to the transient simulation. For the transient simulation, here. So we have for this transient simulation example, I have created 4x4 unitary transformer. So this, what you see over here is basically a kind of mesh. It's a 4x4 unitary transformer. On the left, you can see 4 different lasers sending in 4 different channels, and this goes through this filter. And this whole 4x4 unitary transformer comprises of 6 basic unit lengths. What is a basic unit length? It's basically a combination of 4 different directional couplers. So the input directional coupler and the output one, these are the 3 dB couplers. And these 2 directional couplers are in the bar state. That means all the power which is coming through this port, it goes all the way through and passes through this port. So none of the power is being cross coupled. All the power is going in the bar state. So these are the bar couplers basically, and the combination of these 4 directional couplers basically form 1 basic unit length, and these 6 basic unit lengths form this whole unitary transformer. Now, the purpose of this is to like this filter can be used as a channel, and these filters are being fabricated and being used in various applications like quantum computing, in switches, and different DMUX applications. So the way it works is like on the left-hand side, you since there are 4 different lasers sending in 4 different channels. So this is channel 1, and this channel will be obtained here in the last in the output 4 here. To measure the outputs, we are using the photodiodes, and we have a voltage source to drive the photodiode, and there's a resistor to measure the voltage. And so the first channel will be received at the output 4 over here, and then the second channel will be received at the output 3, and so on, and third input channel will be received at the output 2. So this way, this is like a waveguide mesh. It can be an n by n unitary transformer as well, but in this case, I've just used 4x4. Now, once you have another thing is, as mentioned in the OptiSPICE standalone as well, like if you look at the electrical devices and their connections are in blue, and all the connections between the optical devices, they are all in orange. So that helps you to distinguish between the electrical and the optical devices in your circuit. Now, once your schematic is set up, then we go to the simulation settings, and we go to the transient analysis. Here I have set the stop time to 1.4 nanoseconds, and the maximum time step is sorry, is 10 picoseconds. And once your simulations are set, you hit run simulation. Yeah, as expected, it is giving the errors again. So it's because of the same extracting issue. For some reason, it's not extracting the netlist properly. And let me tell you, like, this error occurs only for the JPEG for at the moment. The rest of the devices are extracted perfectly. So sorry. If we go further down here you will see for the directional coupler, it's missing the two commas, and then I think, yeah, that's it. So we don't have to do it for all, and since all the devices are directional couplers, we just do it for one. We save it, hit run, and now it will run the simulation. And here you can see the progress bar. So it's gonna take a couple of seconds. So you see here, it opens up the Tanner waveform viewer, and you can see this in the graphs being, the response being recorded. And okay, so now the simulation is completed. Now, if I go back to the circuit, let's say the channel 1, and let's see these lasers are basically driven using the bit source and bit generator. Now let's look at the pattern of the first channel. So it's 0 1 0 1 0 0 0, and this we expect to come out of channel 4 over here. Sorry, output 4 over here, and the name of this is N72. This one, N72. If we go back, so here it is. It's 0 1 0 1 0 0 0, and then if I show you one more, the output 3 is N71, and let's look at the bit pattern of the second channel. It's 1 1 1 4 times 0. Now let's go back, and 71. Yeah, so 1 1 1 0 0 0 0 1 0 1 0. So you can see that channel 2 is being obtained at output 3, and same goes for the rest of the channel. So this shows that how each of the channel is frequency channel is transferring from one stage to the second stage to the third stage, and then all the way out. So this is a waveguide mesh unitary transformer. Now, so yeah, that's an example for the AC simulation. I will be showing later in the webinar. I'll be showing the how we can extract the netlist from the mask layout, like from the SEdit, and then extract the netlist, and then create a subcircuit out of that, and then use that subcircuit again in the SEdit here to run the simulation. So basically, you can test your your chip level circuits. You can create a sub-circuit and then run it in the SEdit to make sure your responses and your results are accurate. So I'll be in that particular example. Again, I'll be showing you the same circuit, but I won't be showing it right away because that simulation is going to take a long time. So I'll leave that for the end. Yeah, I'll be showing the same filter again. Now moving further, next thing I would like to show you is how we can use the SParameter elements just like in OptiSPICE standalone, we have the SParameter ports here. So like this, if I go to the OptiSPICE device library, and here you can see SParameter 1x1 port, 1x2, 2x1, and 2x2. So this is this whole filter is basically a 2x2 flat top filter, wherein I'm using the SParameter ports. This is 1x2, and if I look at the properties over here, so in this port I have uploaded the 1x2 MMI SParameter. So sorry, I've specified the path for this MMI SParameter files. If I go here in the SParameters here, so these are the text files of the SParameters in touchstone format. So it is 1x2 MMI 50/50. It is 2x2 50/50, and 2x2 85/15 splitting ratio MMI. So and all these SParameters are in touchstone format. So you can see here that I have uploaded these files over here. All you have to do is just specify the path, the correct path in order for them to operate. And yeah, in the same way, this is again for 2x2, and then this is for the 85/15, and so on. And then there are different waveguides which basically form the MZI kind of structure over here, and there are different lengths. So if let's say if I select one of the waveguide on the right hand side in the properties, you can see the length over here. You can mention the length. Then there is refractive index imaginary here. You can set the value. You can set the refractive index real value, and also there is an option of setting the refractive index file here. So here, instead of using one specific refractive index, I'm using a data of a waveguide, which is the ineffective data as a function of wavelength. And you can see here that I have mentioned the path for this waveguide ineffective data. And if I show you in here in the folder, this is the data. So you can see the ineffective values as a function of wavelength. So this is so this is a really interesting feature that you can extract the information of your modes and the ineffective, and you can use them in the circuit by just uploading your text file over here. So there are different, as you can see, there are different waveguides over here which form the complete circuit. And of course, there are some at the end, there are like these lengths are really like there are different lengths in order to have a correct phase shift of the output response and to provide accurate flat top response. And at the output, again, we are using the optical terminators, and then we are using the probes. Again, in the probes, we have to mention the correct name of the device to which the probe is connected, have to mention the correct direction, and port is, and the correct port. So that's the the filter, that's the circuit for the 2x2 flat top filter. On the left hand side here, we have the laser, and it is driven by the AC source. And so we'll be running the AC simulation for this particular example. So we go to the setup simulation, we go to the AC analysis tab. For this case, I've set the sweep type to linear, and then I've set the start and the stop frequency. It is 193.5 terahertz, 194.5 terahertz is the stop frequency, and set the number of frequency points. Once the simulation is set up, then we hit the run. We hit the run simulation. So now you see here, this simulation is completed, and there was no error. Why? Because we just use we are using the just two devices, the SParameter element and the waveguide, and they are both from the OptiSPICE device library here. So the netlist which is extracted is accurate. And if you look at the response, here is the transmission response coming out of that filter. You can see the two different channels which are flat top. On the x-axis we have the frequency, on the y-axis we have the transmission in dB, and also you have the phase information for your response. So this is for the S parameters. So this shows like how you can how it helps you to extract your S parameters for your devices, and then you can upload and have a circuit level simulation for your whole circuit. Now moving further, I will be showing you some complex examples, like for example a ring gyro, which is a very good application for where we can demonstrate that how well the OptiSPICE can handle the feedback loops. If we go to the OptiSPICE circuits, here in the example you can see the fiber optic gyroscope. If I open this one, yeah, so that's the entire circuit. It looks pretty complex, but I'll just break it down for you. So just for the sake of explanation, like I'll quickly tell you what's the theory and the background behind the operation of the optical gyroscope. So this gyroscope is basically made of generally made of fibers, and these days it's also made of ring filters. So these optical gyroscopes are basically based on the Sagnag effect. So the governing principle is the Sagnag effect actually. And what is Sagnag effect is like it's when a beam is injected into the ring filter, or in this case the fiber, then due to the Sagnag effect, one beam experiences if the ring is not moving, if it's constant, then if it's static, then both the paths going into the clockwise and to the counterclockwise, they both experience the same phase shift. Whereas if you slightly move the ring, then one path experiences a longer path. The light traveling in the, let's say in the clockwise direction, experiences the longer path in comparison to the light traveling propagating in the counterclockwise direction. So and this change can be measured using the phase difference between the two beams. And using this phase difference, we can detect the rotational speed of the fiber gyroscope. So based on the Sagnag principle, we have created this ring gyroscope. as you can see over here, let me break it down for you. So here we have a laser source, which is the bit with a V pulse. And here we have set the pulse width, the rise time, and the period, and the fall time. And the signal is sent through a 3 dB splitter, and the light propagates through the phase shifter. So all the optical elements are used from the OptiSPICE device library over here. So it passes through the phase shifter, which introduces a phase shift. And then the signal, it goes through another set of 3 dB splitters, and the light then propagates into the ring over here. So basically, the first splitter is used to create a clockwise and a counterclockwise propagating waves in the ring resonator. Then this phase shift elements, they are used to change the phase of an optical signal using a voltage node, basically. And these phase shift, what they do is basically these phase shifters, they introduce a linear increase in the phase over time to shift the carrier frequency of the clockwise and the counterclockwise propagating waves. And this shift in the frequency, basically it is used to keep the carrier frequency of the clockwise and the counterclockwise propagating waves matched to the resonance. So this phase shift here introduced here it's really important to keep the frequency to track the carrier frequency and to lock it. Then from here the signal, it goes to through the rings over here. So these are the rings. So here we have created 2 rings. Basically we are mimicking the path of the ring. So signal coming from this end, it goes here, and then it goes in the clockwise direction here. We are using the waveguides here. If these are the phase shifter waveguides which we are using. Here on the right hand side in the properties, if you see, there is a property of DLDV, which is basically the amount of change in the length which happens by changing the voltage. So here we have a voltage controller here, which helps in changing the length, and this change in length in the waveguide basically introduces the shift. So yeah, and also we are using the optical isolator, and these optical isolators basically helps to maintain the direction in one path for each of the ring. So in the right ring, we observe the clockwise path, and in the left ring we observe the counterclockwise path. And then the signal coming from each of the ring is transported further to these photodiodes over here. So these are basically the like this unit is basically for the resonance detection. The signal coming out from the clockwise goes through the balanced photodetector here. You can see the 2 photodiodes, and then it generates a vector signal here, which shows the it generates the vector, the error signal basically. So the 2 separate resonance detectors are used for clockwise and counterclockwise propagating optical signals. And the balance detector here, the balance detector output, it changes as there is a shift in the resonant frequency, which is due to the change in the length of the waveguides of the ring. And when there is a shift in the resonant frequency, the output of the balance detectors, it will shift away from 0 volts. So I'll show you what happens over there. And then there is an RC filter over here, this one. This RC filter, what it does is like it removes any unwanted noise in the signal, because that can be that can give you the inaccurate results coming out of the detected signal. So this RC filter is used to filter out the unwanted noise, and then this signal then further it goes into the PID controller over here. This is used to control the feedback phase modulation of the signal, and you can see in the PID controller here we have the KP and proportional and the derivative. So we keep on tuning this proportional and the derivative values until a stable operation is achieved. And so the output of this PID is basically the shift in the angular frequency from the resonance. And then moving further, there's a PID. There's an output PID, so which shows the shift in the angular frequency from the resonance, and the integrator. This integrator following the PID controller, it generates the phase modulated signal that shifts the carrier frequency going back into the resonator. So this signal, if you see this wire, this basically it feedbacks into the resonator here. So this feedback loop is essential for the carrier frequency to track the resonance of the ring resonators, and then finally at the end here. Here we can calculate the rotation speed. You can see the name of the node, V rotation over here, and this from here we can measure the rotation speed, which is calculated from the angular frequency shift. That is like it can be calculated using an equation. There is an equation to calculate the rotational speed using the angular frequency shift. So this way we can measure the rotational. We have mimicked fiber ring over here. We have mimicked the paths, which is a counterclockwise and a clockwise path, and then the signal goes out from the photodetectors, and then it is filtered out using the RC filter here, and then it goes to the PID controller, and the parameters of the PID controllers are constantly tweaked until the stable operation is achieved. And then from this integrator, the signal is fed back to the ring to lock to track the carrier frequency and to measure the change in the phase shift. So this is the overall ring gyro example, which shows the complex circuits, like how and also it shows how well it can handle the feedback loops. Now for this one, we will be running the transient analysis. So we go to the transient analysis. We have a stop time of 7 milliseconds and the maximum time step of 2.5 microseconds. So once the simulation is set up, we hit run simulation. Yeah. So here now we have the plots. Here is the error signal coming out of each of the photodiodes. So like right after the signal is photodiode, we have the vector V error 1. So that's the signal, like that's the V error 1. This is V error 2 for the clockwise and the counterclockwise. So that's what's being obtained here. This is V error 1. And yeah, And then moving further, we have the VFD1 and we have the VFD2. So this is the signal coming out after the. This is the VFD1. Here is the VFD2. Yeah, and that's the. I think there's some lag. So this is the VFD1, and here's the VFD2 signal coming out of the PID controller, and that's what. So this basically gives us the difference, the phase shift difference, and yeah, and then the last one gives us the. And using this phase shift, we can control. We can calculate the rotational speed. And in the end, this one gives us the this one gives us the rotational speed, which is somewhere around 17.19 milliradians per second. So this gives us the rotational speed. This plot over here at the end. This one. So this after at the end we can calculate the rotational speed. So what we have done is we have used the adder here to simply add the two signals, and then we can calculate the difference, and then we can calculate the rotational speed. So this gives the rotational speed over here. So this ring gyro is basically like it's a very good example to show how the feedback loops are handled. Also, this can handle the reflections as well. Now, for the reflections, I'll be showing you an example of the LiDAR. So here in the LiDAR, maybe I'll ask Chem here to just come in, and maybe he can explain you the application of the LiDAR here. Chem?
Yep, I'm here. Okay. So the way this LiDAR works is you have to chirp the signal. So we induce a linear increase in frequency that the laser is outputting. And then afterwards, we split the signal into two. One of them stays normally within the chip, and then the other path, you'll see that it goes outside the chip, and then on the right side, there's a target. So the signal hits the target, comes back, and then at the bottom, we use the photodiodes and the directional couplers to interfere the signal that just came back into the chip, and then it was traveling, and the signal that was traveling outside. So both of the signals are chirped, but one of them is delayed. The one coming back from the object, the signal reflected back from the object has a time delay on it. So when you interfere the two, what you end up with is a beat signal, because there is a linear increase in phase for both, linear increase in frequency for both. And when you subtract the two, you end up with a constant difference between the frequencies. So then the difference between these frequencies is proportional to the time traveled between the chip and the target. So when we look at the beat frequency coming out from the photodiode, we can actually measure the distance traveled by the light. So this is the basic principle of this LiDAR simulation. So you can go ahead and run the simulation, Saurabh.
Yeah, just to add on to it quickly, like so here we are using the frequency control laser, and like Chem suggested, so we will ramp up the frequency, and it's control using the pulse. We have set the frequency to be ramped up between 193.1 to 193.2 terahertz, and then here we have to get the signal, to get the feedback signal, we are using the circulator here, and rest are all, and that's the target from where the signal will hit and get and reflected back. So yeah, so that's the circuit. Now, if I go to the simulation settings in the transient analysis, we have set the stop time to 2 milliseconds and the maximum time step is 0.2 microseconds. If we run the simulation, I expected the error. That's okay. Again, it's the error because of the improper extracting of the netlist. Yeah, so we have to. Okay, so that's the signal coming out. Like I think that's the signal which is the difference between the reflected signal and the signal which stays on the chip. All right, Chim. So we are measuring the difference here.
Yeah, so we're measuring the signal coming out of the two photodiodes. So that's where we're getting the beat from. And this is, so the signals are mixed right before the photodiode and then added together. The balance detectors remove the DC offset. So that's why you're seeing everything centered around 0.
Right. Okay, so yeah, so that's the example for of LiDAR, which shows.
You know, let's do one other thing quickly. If you want, you could change the length on the waveguide outside, which mimics the signal traveling in air, and we'll see that maybe increase. Let's see, where's the length? So make it so right now it's 3 meters. You can make that 5 or 6. And run the simulation again, we should see the frequency increasing with distance. Yeah.
So yeah, so we can observe the change as we change the path, the length.
We first see the doubling. The other thing is it depends on how we organize the chirp. There's the rotation is either the rotation for the sign is either counterclockwise or clockwise. So that's why you're seeing this dip in the middle. But over when you average it over a very long distance, you'll still get the correct frequency. Yep. So you can move forward.
Okay, thanks, Jim. So Now, so yeah, this application shows that our OptiSPICE plugin engine, it can very well handle the reflection simulations as well. Now, moving further, now I'll be going back to the SEdit now, and I'll be showing you how we can create a mask layout in the layout editor, and in the mask layout tool, and then how we can extract the netlist for your mask layout, and then fed it back into the SEdit and run the simulation and test your layout, whether it's working fine or not. So in the Tanner platform, we have the mask layout tool, which is called as SEdit. So let's open the SEdit. Again, we have to load the library definition file. Yeah, so once it's loaded, here you will see the JPEG standard library, and in the library we will see all the elements present in the in the JPEG library. So just to repeat that, like all these libraries are what I have shown you here in this one, and let me just pull up the actual circuit simulation which I just showed you guys. So just to refresh, so this was the 4x4 unitary transformer, or a waveguide mesh unitary transformer, you can call it. So it comprises of 6 basic unit lengths, and each basic unit length comprises of 4 directional couplers over here. And since I use the JPEG devices over here, so I'm going to use the same JPEG devices in the mask SEdit tool. So here in the mask layout tool, what you see over here is the same circuit. If I just zoom in, so that's the 1 basic unit length. Let me zoom in further. So you can see the directional coupler here. And if I just open the properties for this directional coupler, you can see the length. So this is the same length as I showed you in the SEdit for the 3 dB couplers. So it's 46.647 microns, and same is here, 46.6%. So these are the, so I've set the length so that they behave as a 3 dB couplers. Then so the input and the output couplers are the 3 dB, and then these ones are the couplers in the bar state. If I look at the properties again, you can see the length, which is 126 micron, and which is similar to the length over here, 126 microns. So yeah, so that's the 1 basic unit length, and then if you see here, so that's the second one, and then we have like in total 6 basic units. So that's the whole filters mask layout. And as you can see here on the right hand side, here I'm using the edge couplers. So this edge coupler is already one of the element in the JPEG standard library for coupling in the light. So I'm using this edge coupler 1550, and then we have these straight waveguides like this, and we have bends to form the circuit. So there are a lot of in total there are a lot of elements here which complete the mask layout. So these edge couplers. So this is the input channel 1. This is input channel 2. This is input channel. Sorry, this one is input channel 3, and this is input channel 4. And for the outputs, that's the output 1, output 2, output 3, and output 4. So that's the mask layout for this particular filter. And now I'll be showing you how we can extract the netlist from this mask layout. So we go to tools, we go to photonic tools, and we hit extract netlist here. Now this will open this window wherein you have to type the path where you want to save the netlist. So let's say we want to save it in the in this path, and let's say the file name is test10, and so we have defined the path for saving the netlist, and now we have to make sure that we check this box for write as subcircuit, because then it will extract the netlist and then it will export it in the subcircuit definition format. So make sure that you check this box, then hit OK. And now if we go back to the folder, and if I go to the LLD netlist here, that's the test 10. So this will open the netlist in here. So here you can see the 4x4 entry transformer exported by LEdit, and you see this is the subcircuit definition for this particular unitary transformer. And here you can see the list of all the elements, all the devices which are linked together. So let's say, for example, this is a straight waveguide, and then this is a band, and these are the connections here. And so all of these are connected to each other, and it shows the entire list of all the devices which form the mask layout. So as you can see, there are a lot of elements. Now, using this netlist, now we will create a subcircuit, and then we will use that subcircuit in the SEdit again and run the simulation and test our circuit. So instead of doing it again, I have already created it. So now if you remember, in the beginning I told you that if we go to the simulation here, and if we go to the general here, I have uploaded the header files. So what this header file is basically a text file. This is basically a text file wherein I have just copy pasted that extracted netlist, and I've named it here subcircuit over entry transformer version 3, and then there is a list of all the elements, and it ends here. Now the thing is, we have to name the ports here. So otherwise the like the subcircuit doesn't know which is the input and which is the output port. So what I've done is I mentioned the ports here: optical 1, optical 2, 3, 4, and same goes for optical 5, 6, 7, 8, which are the output ports. And these let me just show you. If I select, let's say that's the output 4, opt 8 is basically output 4, and you see here this one is connected to one of the edge couplers, and the same way all these ports here, these are connected to the edge couplers, which are the inputs and the output ports. So we have to mention these ports in correct order, otherwise that can mess up the circuit. So once the ports have been defined and everything is defined, then you save this text file, and we have to upload this this header file in here in the include file section. I have already included it, and then now let's say we have to create the subcircuit of this. So let's say I chose the my circuit library. I will right click, I'll go to the new view, In the new view, in the library, make sure you have selected the correct library. Then in the cell, let's say we give you unity transformer underscore test 10, any name, and then view type is schematic, hit OK. And then here UT test 10, and then right click again, open new view. Then again, make sure your library is correct. Your cell name is correct. It's the same for the as you created for the schematic. Now, from this drop-down menu, you select SPICE, and in the SPICE, when you hit OK, it will open up this window, and you have to paste your copy paste your this whole subcircuit definition or the netlist which you have extracted from the mask layout. You select that, copy, and you have to paste it over here. And once it's pasted, then you go to cell, go to generate symbols. Now in this window, again, make sure your library is correct. Then your cell name is correct. View, it by default, it remains schematic, and then the target view name will be symbol. Now here we have to name the ports. So for this, on the left hand side, we'll have we have opt1, opt2, opt3, opt4, and same goes for the right hand side, opt5, opt6, opt7, opt8. And then hit replace, just to make sure the ports are right. Yeah, on the right hand side. Okay, and then hit replace. Yeah, and that creates your subcircuit, and basically this will behave as your filter. Now, once it is created, we have to make sure that the ports for this subcircuit are all optical. So what we have to do is we have to change them to the optical. So we select each port, and then in the type here, we select the photonic. And this will, now you can see it has changed the port form. Now it is converted to photonic, and similarly, we have to change for each one of them. And once they are changed to photonic, and then all you have to do is just hit save, and this will save everything. So now you have your symbol here, which can like you have a subcircuit, and this can be now used to test your circuit. But before that, generally, like sometimes it might give you a bug or error before running. So generally what you do is you select this schematic and the SPICE files, and you delete the views from here, and so that will, and then hit Control Save again. Now you have your symbol over here, and then you can use this and create your test bench and run the simulation and make sure that your mask layout or your schematic is working fine. In this case, since I have already set it up for you, I'll open this one. So this is again this is the subcircuit. If I just zoom in to show you, yeah, that's a 4x4 unity transformer. It has 4 ports on the left, 4 ports on the right, and it's all set up. So this is the channel 1 with the same bit pattern, and then this is channel 2, channel 3, and channel 4, and we should expect the input channel 1 coming out from the output channel from the output 4 here, and to measure the signal we are using again the photodiodes and the resistor and the voltage source to drive the photodiode. So we should expect the signal 1 coming out of the output 4, signal 2 coming out of output 3, and so on. So once the schematic is set up properly, so we go to the simulation settings. Here I'll go to the transient analysis. I've set the stop time to 0.8 nanoseconds and the maximum time step to 1e-14. Since the time step here is very small, so this thing is going to take some time. Let me run. Yes, so it's running now. Here in the TSpice, you can see the progress here. So you see it's taking a lot of time because there are a lot of devices. There are 116 devices and 2093 nodes. So in total, it's a very heavy circuit. It's going to take some time. We can wait until then, and in the we can from my end, I think, yeah, that's all from my end. Now maybe we can take up some questions, and in the meantime we can come back to this simulation later once it's finished. I can show you the results for that. So yeah, now I think that's pretty much. Chem, do you want to add on something here?
No, I think we're all good.
So if anybody has some questions, yeah, please feel free to go ahead. You can ask.
You can use the raise hand feature of Zoom, so we can give everybody a chance to speak. Niharika, go ahead.
Yeah, thank you for the presentation, Saurabh. It was very interesting to learn all these capabilities about the software. So my question is not directly related to OptiSPICE. I was just wondering, this GPIC library that you have used in your, like, the devices that you picked up, the bend and the waveguides and everything, is it related to some foundry, or I mean, what are the devices in this library?
These devices are not directly linked. This is Jem speaking. These devices are not directly linked to a library. This is the example library that comes with Tanner. So what we did is we matched them with our own devices to, you know, prepare demos pretty much.
Mm-hmm.
But they're not directly linked one-to-one to a physical layout.
Okay.
I mean, they approximate somewhat how it should behave, but it's not exact.
Okay. Yeah, that's what I wanted to know. Thank you.
But we have different PDKs that we support right now. We have 4 of them that we have been working on. We have HHI, AIM Photonics. We have Ligentech that we're working on, and then CNM. It's a fab in Spain.
Okay, that's very interesting to know.
But
And
if you have interests in other fabs, please let us know. We can get in touch and see if we can work with them as well.
Okay.
We would like to have support as many PDKs as possible.
Mhm. Okay. So these circuit simulations that you showed us, like, how is it different from the interconnect simulations that we perform?
So the main difference is that our models directly put they directly share the set of equations with TSpice. So that's why that's the main difference. They work within the same simulation engine, and they
Okay.
converge very easily when you're dealing with the electro-optic feedback loops.
Mhm.
It is essentially, so we're not using two separate simulation engines, we're using a single simulation engine that runs all the devices. So for example, when we're running a transient simulation, we have the host engine, which is Tanner, and the host engine dictates certain things that was set up by the user, like the time step, the devices, what kind of devices that need to be in the simulation, etc. On our hand, what we do is we support the optical devices. So when there's an optical device that needs to be instantiated, then the simulation engine calls our piece of code and does the instantiation and the updates as the simulation engine takes time steps.
Okay.
So this is a slightly different mode of operation. I mean, the thing is, I don't know if anyway, I'd rather not comment further on the interconnect, but I prefer to keep it focused on OptiSPICE. But this is the main mode of operation as I described.
Mhm. And for the PDKs that you mentioned you're working with, the devices are based on fabricated, like measured data?
Yes. So we get the
Okay.
data from the fabs directly. If in some cases, if we need more data on passive devices, we sometimes use OptiFTTD to run the simulations and generate S parameters for them.
Mhm. Okay, that's very interesting.
Okay. We're Saurabh, we're waiting on the simulation to complete. Is there a simulation running in the background?
Yes.
Okay.
Yes. You can see the progress here. Yeah.
Okay. So we have some more time to take questions. If anybody's interested. Another thing I would like to mention is you can always reach us and we'll be happy to provide evaluation version of our software for either the standalone version of OptiSPICE that we have demonstrated yesterday or the plugin version that we have demonstrated today. Like I said earlier, please let us know if you are interested in a particular process with a particular fab. We'll definitely be interested in getting in touch with the fab to see how we can collaborate in supporting their PDKs and so that the users can use OptiSPICE plugin for designing photonic integrated circuits. And we're also looking into supporting other PDK, other EDA vendors as well. So we have some work going on, which will be announced later when it's ready. But the idea of OptiSPICE plugin is that we support the PDKs. We just generate the compact models based on the data shared by the fab, the device data shared by the fab. And it is going to be, once we do that, because we use the same piece of code for all the plugins, for all the separate connections with different EDAs, then it will be automatically available for all the platforms that people want to use. So it's not this plugin is right now it's released with Tanner, but in the future we're going to release it with other large EDA vendors, right? Like similar to Tanner. I think the simulation is almost complete. Yeah.
So if we just quickly go back and look at the bit pattern for the channel 1, it's 010100, which we should expect here at N8. Let me just yeah, so it's 010100, and then the same way, if we look at the bit pattern for channel 2, 11140, this we should expect at N7. So yeah, 1110000, and yeah, so and so on and so forth. So the same goes for the N6. That's the this will be the input channel 3, and this is the input channel 4. So yeah, so like I said, this way you can validate your mask layout schematic, and this shows that how you can create your sub-circuit out of your mask layout, generate like extract a netlist, create a mask layout, create a sub-circuit, and then feed it back into the SEdit tool, and you can run your simulation. So this yeah, so this basically concludes my presentation over here.
Yeah, thank you so much.
So yeah, and so over to you, Chairman Ahmed. Yeah, please.
Yeah, is there any questions from the audience, please? Okay, I think in that case we can end the webinar. Thank you very much, Saurabh and Chim from Optiwave. If you're interested in obtaining trial license, please contact me. I'll make sure that I get you trial licenses from Optiwave. Thank you very much again, Saurabh and Chim, for this informative session. It's very useful. And thanks everyone for attending. Thank you. Have a good day.